by giving a little bit of background on water quality. You know, how do we think about it from a research perspective? How do we think about it here at WRI? And then I'll hand it over to Matt in a couple of minutes. So to get us thinking about water quality, I did want to ask the students in the room, what are some examples of water contaminants? You know, when you think of a water contaminant, what is it that comes to mind?
Heavy metal.
Heavy metal, yep, that's a good category.
First thing that comes to mind.
Lead.
David? Yep, everyone has an answer, right? Water contaminants. So
Plastics.
right, plastics.
Yep. Metals, plastics, anything else?
Like bacteria or like disease.
Good.
Sure,
Bacteria.
yeah.
PFAS? Is that how you say that? PFAS.
PFAS,
Yeah.
yeah. That's a hot topic right now. Yeah, so there's quite a range there, right? There's a variety of different ways in which we can think about water quality contaminants. And each of those contaminants, you know, has their own different set of risks and characteristics associated with them. So when we think about water quality, that's really going to change depending on the contaminant. And we might think about some different questions in terms of, you know, what contaminants are at risk of being present. For example, if you're in a public school, you might be concerned about the lead in the pipes because students and children in particular can be at risk. If you're downstream of an airport, for example, maybe you're worried about PFAS, right? That's a flame retardant and can enter into drinking water. And besides that, you're also going to want to think about concentrations, right? If something is very small in concentration, maybe it's not a huge concern. But if it's above some of those thresholds that we know are, you know, at risk of posing toxicity, and then we need to start paying attention. And then you might think about, okay, well, we have, you know, a risk for different contaminants. Where are they coming from, right? What's the source? Is it a diffuse source throughout the landscape, or is it a very targeted source? And then think about where they're coming from, where they're going in the environment, what's the cycling that's driving these contaminants and how they move through the environment, and why, you know, what are the stimulating environmental factors for some of these contaminants? So my background's in mercury, so sometimes I think about, you know, where are there reservoirs? Are there wetlands? Are there these locations that we know where mercury can be mobilized into the environment very readily? And then finally, we also want to keep in mind who's going to be impacted, right? Why are we concerned about this at all? Are there sensitive populations like children or women of childbearing age? And then finally, who's responsible, right? Who's going to deal with this? Who might clean up or pay or manage this problem, and ultimately be in charge of some of that decision making. And some other considerations more from maybe research perspective, we might think about point versus non-point pollution. This might be a familiar term to some folks. Point sources, those are often from you know, factories where there's a direct discharge into the environment, or a vessel like a barge coming up the river. But then you also have non-point source pollution, and that can be a little bit trickier because it can be very diffuse throughout the landscape, throughout the watershed, from several different farms throughout the landscape, or different roads, or simply just an urbanized landscape, right? So it's tough to really pinpoint exactly where that pollution is coming from. And that's sort of on a spectrum, right? There's a whole kind of range of point versus non-point pollution. It's also important to think about change over time. The source or the sort of input into the water system might vary depending on the day. If there's an extreme event like a storm, for example, in my own work, sometimes we're concerned about flooding that might increase the input of mercury into a system. It might also mobilize existing contaminants that are present. And then finally, we also want to think about spatial differences. So a lot of our programming here at WRI is actually watershed based, and that can be pretty convenient actually for thinking about water quality and other water resource problems, because watersheds are going to differ. So my work focuses on the Great Lakes. So a lot of my thinking is in context of that system, which is going to be very different than a different watershed like the Hudson River watershed. So these are different things we need to keep in mind as we're assessing the risk ultimately of water quality problems in our area. And then finally, at WRI, water quality is one of our main themes. And this is just sort of one way in which we kind of organize our work. This is a list of different contaminants we currently work on. And we can think about contaminants falling into a couple different categories. You may hear legacy versus emerging contaminants. So legacy contaminants are those that have been around for a while. They also tend to bioaccumulate, to not break down. And even though we may have researched them for a while, we've been working on managing them for a while, they're still present because of some of their legacy contaminant characteristics that keep them present in the environment and in systems over time. Emerging contaminants are kind of on the other end of the spectrum, and they're sort of new. We can call them new contaminants, right? They're new in the sense that we have either recently started putting them out into the environment, and or we might simply just be starting to understand them and really kind of get into what their risks are in terms of toxicity, how they cycle in the environment, etc. And a third category are geogenic contaminants. So we're going to hear more about that in a second, and that includes manganese. And this is a bit unique in the sense that they come from geologic formations, so it's kind of naturally occurring. And because of that, it presents sort of a weird situation from the perspective of who, right? When we start thinking about who is responsible, it's no one's fault really, right? It's sort of this naturally occurring contaminant in a way. So then we have to think about, well, who's responsible and who really has to deal with this situation that poses a risk for public health via drinking water. And in this case, we might think about drinking water purveyors who actually can enact rules and regulations around drinking water. So in this case, the city of Ithaca is very interested in Matt's work, and that might help inform them, making some future decisions down the line. So before I go too deep there, I'll pause and see if anyone has any questions or comments before I turn it over to Matt.
Thanks, Evie.
All right, so I will get started then. So thank you again for the opportunity to be here today to talk about some of our work on manganese in the Ithaca Reservoir. Thank you also, Evie, for that really nice introduction. And actually the discussion actually did a nice job teeing up some of the topics that we'll be talking about. So let me get a laser pointer here. Okay. So first I want to really acknowledge the research team that was involved in this research. I especially want to thank the staff at the Ithaca Water Treatment Plant, led by Roxy, who's here today. The treatment plant has been just an amazing community partner in performing some of this research, and I know that my research group and I are really grateful to them for all the hard work that they've done here. And I also want to thank a number of students at Cornell, led by my PhD student Yi Sang, who's also here, and then also a number of undergraduate and graduate students who have contributed to this work. And for funding, I want to thank the Water Resources Institute as well as the Einhorn Center at Cornell. So yeah, we're talking about manganese. We're talking about a geogenic contaminant here. And a lot of the impetus for this work began in the summer of 2016. Some people were living in Ithaca at this time. I know many of the students were not living in Ithaca at that time, but if you were in Ithaca the summer of 2016, and you were living in a part of the city that gets its water from the Ithaca Reservoir, you would have seen things like this, like really discolored, brown water coming from your tap. And there's a sort of long story behind this that's sort of a little bit too complex to tell right here. But basically, it's resulting from the fact that there were high levels of manganese in the water column in the Ithaca Reservoir at that time, and we'll talk about why in a few moments. So manganese is, it's something that's, it's in rocks, it's in minerals, it's always there. But what can happen is that the way that we humans then manage different aquatic ecosystems can lead to the mobilization of these things from, rocks and minerals into the aqueous phase. That's what happens with manganese. There's also an analog with what happens in arsenic in groundwater, where there can be a lot of arsenic in the geological media. That's not necessarily a problem. The problem occurs when the conditions change in a way that mobilizes the arsenic from the solid into the aqueous phase, so that it then moves with the water, and if the water is taken up. Okay, so traditionally manganese has been regulated by the EPA more as a sort of nuisance contaminant. Obviously you don't want to see things like this in your house. It can stain your appliances. It's a serious issue for water. It hasn't traditionally been viewed as necessarily like a health threat, although around the world, governments are starting to implement lower regulatory standards for manganese, including Canada. So I think there's a growing awareness that there are human health related impacts of manganese exposure. Okay, so why is there high manganese in the Ithaca Reservoir? So we have to go all the way back to 1903, 120 years ago. And what happened in 1903? There was a really actually kind of serious and actually pretty famous outbreak of typhoid in Ithaca. And earlier, some of the students were mentioning pathogens as contaminants, right? Like bacterial or viral pathogens. And at this time, engineers, water treatment utilities were primarily focused more on these pathogens and less on some of these like chemical contaminants. And in 1903, there was a really serious typhoid epidemic. Actually, one of the worst and also one of the last serious typhoid epidemics in the United States occurred in Ithaca and killed 82 people, including 29 Cornell students, which is actually really horrific if you think about that. That's a really, really, really awful event. And what it led to is the realization that there needed to be a more protected and safe water supply for the growing city. So the Ithaca Reservoir was constructed at that time. You can see some of these cool old photos, this old, construction equipment here, and then building the 60-foot dam at the base of what became the reservoir, which is what created what we have today, which is the Ithaca Reservoir here, created by the construction of that dam in 6 Mile Creek. Okay, so here's a map of the reservoir. 6 Mile Creek enters here. The southern and southeastern part of the reservoir is relatively shallow. And then at the northern part of the reservoir, there's this deeper basin here that's about 25 feet deep. Okay, so it's still not very deep when it comes to lakes, only about 25 feet deep. And the intake for the Ithaca Water Treatment Plant is located actually near the bottom of the basin at a depth of about 25 feet. And this is really important, actually, where this water intake is located. And we'll talk about why soon. And the reason for this, you can imagine, right? You want to make sure that if there's a drought or something and the water levels fall, you can still access the water. You don't want your intake to be, near the surface. And then if the water levels go down, you can't get any more water. But there are some other implications for this that we can talk about. Okay, so what happens in summer in lakes is that lakes become stratified. And what that means is that there's a temperature gradient in the different depths of water. The water has different densities, so they don't mix. And what that means is that if you look at this oxygen profile here, the oxygen concentrations at the bottom of a stratified lake become very low, close to zero. So you can have this oxic epilimnium and a hypoxic to anoxic hypolimnium. And what that means is that you can have manganese 4 oxides in the sediments that are just, naturally occurring. And in this case, because this stream has been dammed for now 120 years, sediments are building up sort of in the southern basin of the reservoir behind this dam. So we have more and more accumulation of sediments. There's some geological manganese in these sediments. When we get these anaerobic conditions, the manganese 4 can be reduced by microbial activity to manganese 2 from a solid phase mineral into a dissolved metal. Okay, so this is this mobilization process that we were referring to, and that can then be released into the water column, okay, and then taken up into the intake water for the treatment plant, okay? And like I mentioned, the fact that the intake is located near the bottom is really significant because it means the treatment plant is taking up this hypoxic to anoxic water where there can be a lot of these reduced chemical species that are released from the sediments, okay, in a way that might not happen if the water was being drawn from these oxic portions of the water column. Okay, so lake stratification can be disrupted by storm events or by wind, okay? And this is what we see actually. So if we look at here, some data from 2021, the discharge in the reservoir here is in blue, and these red dots show dissolved oxygen concentrations near the bottom of the reservoir, near where the water intake is. What we can see is that the dissolved oxygen can fall, okay, as the waters become more anoxic and more reducing, and then even a relatively small storm or discharge event can cause the oxygen concentrations to go up again, okay? We see here a really large storm event led to the dissolved oxygen concentrations to go up and then decline here. And then we also see later a period where actually relatively small storm events are effective at increasing the oxygen at the bottom of the reservoir. So one thing that's telling us is that the stratification in the reservoir is relatively weak and easy to disrupt, okay? So we don't have the type of lake system that's like permanently stratified over the course of the summer, but we have a system that sort of develops these transient periods of stratification that are conducive to release of manganese. Those can then be relatively easily broken by storm events, rain events, discharge, high discharge moving into the reservoir caused by rainfall. Okay. So we've established that stratified conditions are important for the release of manganese. The stratification can be relatively easily disrupted by precipitation and discharge events. But at the same time, we sort of are moving into this period where even in this part of the country where we traditionally don't worry about droughts, we're sort of experiencing, somewhat frequently abnormally dry to moderate drought conditions. So here, this shows data from the US Drought Monitor on Tompkins County. This red here, this shows that really serious drought that occurred in 2016, which was related to those high manganese concentrations in the reservoir at that time. But we also see in 2020, and then again in 2022, these abnormally dry to moderate drought conditions occurring in Tompkins County. So if we compare the discharge of 6 Mile Creek in 2021 here in red, in 2022 here in blue, there's a huge difference in stream discharge in July and August. Okay, so actually, with this project, we were pretty lucky in the sense that we got a kind of natural experiment and we could test and we could collect data during a wet year and a dry year and sort of see how this difference in, hydroclimate affects the concentrations of manganese in the reservoir. So what we can see here, so you can see the colors are kind of flipped. When discharge is low, manganese concentrations in the reservoir are really high, including in sort of August of 2022, these really high concentrations measured, almost 2 milligram per liter of manganese measured or 2,000 microgram per liter of manganese measured in the intake waters. These are really, really high concentrations of manganese. Okay. The other thing to take away from that is that we have a lot of temporal variability. There can be really significant day-to-day changes in what the manganese concentrations are, which can be a challenge to the treatment plant staff who have to actually manage this problem. Okay. So, you know, we in the previous slide, we looked at temporal variability in manganese. We can also look at spatial variability in manganese. So here is a depth profile. So what we did is we went out in canoes and we have this water bottle called a Kemmerer bottle that we can lower to different depths and collect water samples from different depths. And so that's what's shown here in July of 2022. Again, this is during a dry period. And we also have a sonde where we can measure things like dissolved oxygen and temperature. And you can see the dissolved oxygen profile on this date shows this very, very classic sort of dissolved oxygen profile for a stratified lake system. Okay, we can also see the temperature gradient here. And there's also a gradient here in pH, which will be important a little bit later. Based on the scale, the pH change doesn't look that great, but the pH is going from over 8 to about 7. So there is a change of about 1 pH unit when we go from near the surface to near the bottom, which is a pretty significant change in pH. And we'll talk about why that might matter in a few slides. But you know, the thing to take away here is that we see near the surface manganese concentrations are low, where oxygen concentrations are high. When oxygen concentrations decrease, we then start to see these really high dissolved manganese concentrations in the water. And again, at depth here, this is where the treatment plant is taking up its water. So the treatment plant is taking up this really manganese-rich water into its treatment system. You know, if we contrast that to what we see in July of 2021, right, when there was this high flow period, we see, you know, manganese concentrations are really low. We don't see these sharp gradients in dissolved oxygen or in temperature because this high flow is causing the reservoir waters to mix, okay? Which is acting to control manganese concentrations 2 ways. One, there's just more dilution, more fresh water coming into the reservoir, right? Refreshing that reservoir water. And at the same time, you know, introducing oxygen, which is basically preventing that reductive dissolution of manganese in the sediments and that active release of manganese to the sediments. Okay, so again, you know, these dry weather conditions lead to these strong gradients in dissolved oxygen, manganese, and pH. Okay, so we also did some analysis of the lake sediments. And this is Olivia, who was a WRI intern a few summers ago. She was a chemistry major at Cornell, and I think her involvement in this project, you know, helped to motivate her to pursue graduate study in water resources. Okay, and I actually got an email from her this morning that she applied to graduate programs, and she has offers from Stanford, Princeton, and Harvard. So she's done well with that WRI internship to sort of propel her into what is looking like a very promising research career. So what we did is we collected sediments from the lake at these different locations, J1, J2, J3, J4, J5, right? And what we saw is that there's more manganese in the sediments in this northern portion of the lake. Okay. We also were interested in studying more details about the chemical oxidation state, the chemical speciation of that manganese. Here, going into a little bit of detail on some chemistry here, I'll try to, you know, make this as sort of accessible as possible. So basically what we did is we took some of these sediment samples and hit them with X-rays with different energies, okay? And what you can do is you can look at the spectra of the fluorescence from the samples induced by hitting them with these X-rays with different energies. And different forms of manganese, different oxidation states of manganese have different characteristic spectra. Okay, so you can see here, this spectra is the spectra that's caused by a manganese 2 species that's bound to biomass. Okay, this spectra is spectra from manganese that's in a manganese calcium carbonate mineral. This is a spectrum for a manganese 3 oxide or a manganese 4 oxide, okay? And I just want to point out that moving into this, we kind of expected that the manganese in the sediments should look like this manganese 4 oxide, okay? So if you sort of read a textbook about the geochemistry of manganese, if you look like, this was my, like, the book I used when I was a graduate student about aquatic chemistry, okay? That would say that you'd expect a lot of the manganese in a lake sediment to be like a manganese 4 oxide, okay? But what we actually saw when we looked at the sample spectra, okay, and when we're trying to interpret this sample spectra, we can do something called linear combination fitting, okay, where we're trying to sort of add these references together in different ways to get the sort of the sum or the combination of those reference spectra to look like these sample spectra, okay? It's difficult to do that perfectly, kind of depends on what types of references you have. But what you can kind of visually see, I think, is that most of our samples don't look like the manganese 4. They look a little bit more like the manganese 2 or this manganese calcium mixed phase, okay? And so the solid line here is our sample spectrum, and the dashed line is our linear combination fit. So again, it's not perfect, but what we are able to see is that most of the manganese in the sediments is actually in the form of manganese 2 or manganese 3. So manganese 2 bound to biomass, possibly bound to dissolved not dissolved organic matter, but organic matter in the sediments, or this mixed manganese calcium carbonate phase, or maybe a manganese 3 oxide. Okay, so there's not much evidence of this manganese 4 oxide. So that was a little bit unexpected for us and surprising. We were especially interested in the sort of the origins of this manganese calcium carbonate phase. Okay, so maybe one last slide here that's a little bit heavy on the chemistry, but so, you know, calcium can precipitate with carbonate or bicarbonate to form calcite, which is the calcium carbonate mineral. Manganese can experience the same type of precipitation and form a mineral called rhodochrosite, okay? And these reactions are important because these essentially reverse that mobilization, okay? So we talked about how manganese can be mobilized from the solid phase into the aqueous phase. That's when it presents a problem because it's mobile in the environment. These reactions essentially can be like the reverse of that, taking manganese from the aqueous phase into a solid phase, okay, where it's not necessarily a problem for like water utilities because it won't be taken up in the water. Now, the thing to mention is that calcium concentrations are usually much higher than manganese concentrations in the environment. So what can often happen is that calcium carbonate can precipitate, but because manganese and calcium are somewhat similar chemically, they're both divalent metals, the manganese can substitute in the calcium carbonate lattice, essentially. So you could almost think about calcium carbonate as it's precipitating. Manganese could co-precipitate with that calcite mineral, and that could be an important sink for manganese in the water column. And this mixed calcium manganese carbonate species is, you know, we saw signatures of this when we looked at that Zanes spectrum, okay? So we were curious about whether we could see evidence for precipitation of these calcium manganese carbonate phases in the water column, okay? So what we did is we combined measurements of calcium, manganese, inorganic carbon, and pH, and calculated what's called a saturation index for different types of mixed calcium manganese mineral phases, okay? And as we go sort of from right to left here, we see saturation indices with an increasing manganese to calcium ratio. So the things we see over here have a relatively small amount of manganese co-precipitated in a calcium carbonate mineral. Whereas over here, we have relatively small amounts of calcium co-precipitated in a manganese carbonate mineral. And so basically what we see is that in this sort of shallow part of the water column, there's evidence that these mixed calcium manganate carbonate phases are supersaturated with a relatively low manganese calcium ratio here, indicating that there is, at least from a thermodynamic perspective, there's a possibility that calcite precipitation could be effective at removing manganese from the water column, which is important. And so we have both some water chemistry data and some sediment geochemical analysis suggesting that that might be happening in the reservoir. And I'm happy to come back and talk about this more if there's any specific questions about how we do that modeling or like what that means. So we can come back now to this sort of conceptual model that we sort of started with. You know, what are the controls on manganese in a stratified lake or reservoir? We started here as this sort of maybe, you know, this is the current paradigm for thinking about manganese dynamics in the hypoxic to anoxic hypolimnium and then the oxic epilimnium. Okay, our data kind of suggests that we may also have this alternative process leading to precipitation of manganese driven by calcium and carbonate, okay, as other factors that could be controlling the solubility of manganese in the system. And then just a few sort of practical take-home points from this part of the talk are that, you know, manganese concentrations are closely linked to stream discharge. Okay, so as we sort of move forward with a changing climate and we think about what that means in terms of, you know, drier summers, it means that that's likely to exacerbate these problems with manganese in surface water reservoirs. Okay, that's true for the Ithaca Reservoir, but it's not only true for the Ithaca Reservoir. Okay, all around the country, we have, you know, water infrastructure that's 100 years old, high levels of sedimentation collecting in these reservoirs. Okay, so we see these problems with manganese release popping up all over the country and probably all over the world. We see high manganese concentrations only occurring below a depth of about 15 feet. And that's related to sort of the depth of the chemocline that we see in the Ithaca Reservoir. You know, and from a very practical perspective here, like a multi-level water intake system would actually be a pretty effective way to avoid those waters with high manganese concentrations. You know, the ability to collect water from a depth of 5 feet instead of a depth of 25 feet, for example. But that's not currently something that is possible, you know, and wasn't designed for when the reservoir was built 120 years ago. And then finally, you know, we have some more sort of like process level insights into what may be controlling manganese solubility in the water column and the role of calcium and alkalinity in the reservoir in sort of acting as almost like a ceiling on what those manganese concentrations could be. Okay. So now I want to move on to, you know, just a few final slides here, and then, you know, I wanted to leave plenty of time at the end for a discussion and a conversation about this. It's sort of a discussion about, you know, what is the Ithaca treatment plant currently doing to manage these high and highly variable manganese concentrations? And I remember, I think I was speaking to Roxy once, who's the watershed manager for the Ithaca Reservoir, and she was saying sort of, you know, to the extent that, you know, when you work for a public utility and you do your job, your challenging job well, no one ever says thank you. No one really ever acknowledges what you do, even though it's really challenging and it can be really hard. It's only when there's problems that suddenly everyone comes out of the woodwork and starts complaining, right? And I think that this is something that occurred in 2016. And, you know, I think that the utility staff responded very quickly and very, you know, expeditiously to develop a sort of solution here, which was to actually dose potassium permanganate into the raw intake water, where it's taken up here. And then there's this pipe here, which is, I don't know, like, Roxy could tell me, 1 mile, 2 miles long to the treatment plant, okay? And as the water's traveling along this pipe, the manganese 2 can get oxidized to this manganese oxide, precipitate as a manganese oxide solid, and then be removed via filtration. Okay, so this works pretty well. There are some challenges though. These chemical oxidants are expensive. Okay, so this is a cost for the treatment plant in terms of money. Also, if you want to think about sort of like the life cycle impacts, the bigger picture sustainability of our water treatment practices, it'd be nice to not have to use these chemicals. Real-time decision-making can be difficult. We talked about the fact that there's high temporal variability. That's sometimes difficult to predict. So, there can be issues where you add too much permanganate, too little permanganate. And what this means is that there can sometimes be an unexpected level of chemical oxidant demand in the treatment plant. And this is specifically relevant for chlorination, because chlorination is also an oxidation process, okay? So if there's a lot of reduced manganese that hasn't been oxidized by the permanganate, this can serve as an oxidant demand on the chlorine. So basically consume that chlorine instead of the chlorine going to oxidize like pathogens or things like that, okay? So basically this sort of like oxidant management can present a problem and can sometimes lead to production of disinfection byproducts in the treatment system. And that was something that was, discussed as an emerging contaminant, disinfection byproducts or DBPs. Okay, and I think this is a really, important example of how, water quality is a systems problem. It's a systems issue. You can't ever really address one part of the system without having maybe unintentional or unintended consequences for other parts of the system. So even though manganese is a geogenic contaminant, and the utility staff is able to manage the manganese problem relatively well, this can lead to some unintended impacts on, say, DBP formation, for example. Okay, so it's a really tough job, and I think while the manganese problem has been managed here, it's still not quite perfect. Okay, so one of the things that we've been trying to do is to develop a predictive autoregressive model to predict manganese concentrations in the intake water based on a set of environmental conditions. We've already talked about the fact that discharge is a really important control on manganese concentrations, and we have some of these other environmental variables that have an effect on basically how manganese is being mobilized in the reservoir sediments. Okay, so we would develop what's called an ARIMA model. It's an autoregressive model. Part of what that means is that our sort of prediction for the manganese concentrations tomorrow are highly informed by the manganese concentrations today or yesterday. Okay, my graduate student Yi has done a great job developing and testing this model. Here's just an example of the model performance from 2021. Okay, so the red dots show our manganese observations. This red line shows the 1 day ahead prediction. Okay, so basically if we have a manganese measurement today and we need to predict the concentration tomorrow, right, using today's manganese concentration as well as weather variables, how well do we do? So you can see it does pretty well. We did know that there was a systematic lag in the prediction, okay? So it was relying a little bit too heavily on that antecedent manganese concentration. And we also then saw that the model parameterized with 2021 data has performed relatively poorly in 2022, okay, unfortunately. And part of that is just because the hydrological conditions in 2022 were so different than they were in 2021, okay? So we're sort of, continuing to work on this predictive model. Yi has been starting to work a little bit with some machine learning approaches, random forest models, artificial neural networks to see if we can improve this, this prediction as a tool that the treatment plant utility staff can use. Okay, and the idea is that this would be made available on a web interface. There already is a web interface for this manganese forecasting tool using the the ARIMA model, but acknowledging that, this model that we built based on 2021 data has not done such a great job with 2022 data. So this remains a work in progress, but I do really want to acknowledge all the hard work that he has done into developing this model and to, doing the work to make this available on a web interface so that, our community partners at the treatment plant staff can access this in a sort of user-friendly way. And finally, I see that there's some things in the chat, so I'm having trouble seeing that right now, but I'll try to come back to that in a moment. Finally, thinking more into the future, into the summer of 2023, we've talked about, predicting these manganese concentrations, but can we do anything to actually sort of prevent the mobilization of manganese? And as I mentioned before, these problems of high manganese concentrations in surface water reservoirs are sort of widespread problems that are occurring around the country. So there's, there are these commercially available, basically bubblers that are commercially available. You can install them near the bottom of a reservoir, use an air compressor and pump in air and use this to try to artificially mix that, the water in the reservoir. So basically try to disrupt that reservoir stratification and try to, essentially prevent the mobilization of manganese during these low flow periods where the reservoir becomes stratified. So that's what's on deck for summer of 2023. We're really excited to continue this partnership with the Ithaca Water Treatment Plant and move from what we've done in the past, which has been primarily characterization, understanding the problem, characterizing the problem, and now in sort of what will be the third summer, looking at some solutions that can try to mitigate the problem. And I also just want to acknowledge that, the important role of the Water Resources Institute in providing initial funding for this project, as well as supporting WRI interns who are able to sort of make important initial contributions to this work. And that's it. So thank you very much for your attention. I managed to not talk too much, so there's some time left for questions and discussion. So I'm really happy to answer any questions that there might be at this time. And thank you again for your attention.
Thanks a lot, Matt. I see the first question is already in the chat, and feel free to leave questions in the chat or just unmute yourselves and ask. So Lewis asked, which method or software was used to model mineral stability?
So that was Visual Mintech was the equilibrium software that was used. Oh, sorry. Yeah, thanks, Yi. So I think we first used Visual Mintech, but then Yi went on to use another software called Geochemist Workbench.
Thanks for joining, Lou.
Hello.
That's Dan, I think.
Yeah. Can I be heard?
Yes.
Yeah, I can hear you, Dan.
Okay. I'm, as you see, Dan Carrick. I'm a geology professor emeritus, and I played with this manganese problem some years ago, but from a totally different standpoint. I mean, that there's a very sizable artesian aquifer underlying 6 Mile Creek. I mean, you work with Sinton to do some of the analysis, and it was sort of a, what shall we say, not a coincidence, but a correlation between high manganese and low flow levels. And as you know, because you looked at the manganese in our well is the furthest downstream that's got any chemical analysis. And the manganese content is significantly higher in that well. I mean, I'm not telling you anything you don't know, than it is in the stream water. And I tried to use manganese because the city measured it and we measured it to try to guess how much of this artesian water was entering the reservoir. And I didn't get an answer that made any sense. But it's number one, it's a significant aquifer. And number two, it is breached at the reservoir because downstream, you have the gorge. Well, if you took the dam away and all the sediment away and looked at the old records, the old topo maps before the reservoir was built, erosion had cut its way down to bedrock about 2/3 the way up the reservoir at least. So there's no doubt that the aquifer is feeding the reservoir. There's also downstream from the reservoir, just downstream, there's a bunch of seeps and springs coming out, which is fed from that aquifer. So, I mean, you haven't talked about that at all. And it seems to me that that's got to be taken into account in your analysis. So,
Yeah.
go for it.
Yeah. Thanks, Dan, so much. Thanks for coming. I don't think we've met before, but I know talking to Roxy and talking to Kristen, I've been aware of your work, really important early identification of this problem and work on this problem. So yeah, so maybe providing a little bit of background, and you're right, I didn't include some of this in the slides. There's a confined aquifer, upstream of the Ithaca Reservoir, and a number of people who live in like Caroline, near German Cross Road, draw their groundwater from that confined aquifer. And that confined aquifer can have relatively high manganese concentrations in it. I believe up to, if I recall correctly, Dan, maybe 300 microgram per liter in your well, if I remember that correctly.
Your analysis was higher than the USGS analysis, but it was well over 100. It was under 100.
Yeah.
I didn't look it up, but it's high.
Yeah, no, it's definitely high. It's sort of, above what would be, I think, if you think about that Canadian government new health-based recommendation of 120 microgram per liter, it's roughly like 2.5 times that number. So that's pretty significant. When we first started this project, we were really interested in trying to constrain the contribution of groundwater discharge from that confined aquifer into the manganese reservoir as a source of that manganese. And we also did some water isotope analysis to try to trace how much water in the reservoir is coming from that confined aquifer versus how much is coming from stream flow. I think ultimately one of the reasons that we didn't pursue that more fully was that, the highest concentration that we measured in that groundwater was at your well, which I recall was about 300 microgram manganese per liter. Okay. And in the summer, we're routinely measuring concentrations of manganese in the reservoir of greater than 1,000 microgram per liter. Our highest numbers are something like 2,000 micrograms per liter. Okay. So my thinking was that even if 100% of the water in the reservoir was coming from that confined aquifer, we would still only be seeing concentrations of about 300 microgram per liter. But we're seeing concentrations that are 5, 6, 7 times higher. Okay, so that's sort of what led to having more of a focus on the sediments and the chemical speciation of manganese and the release of manganese from the sediments. Okay. However, I think a really important thing to point out is that absolutely our region is geologically rich in manganese, and that's the ultimate source of the manganese in the reservoir sediments. Why is there so much manganese in the reservoir sediments? Because there is, manganese in suspended sediments, possibly dissolved manganese that's then being oxidized at some point in the reservoir. I believe some of that groundwater sort of comes to the surface near Caroline and then sort of goes subterranean again. And actually in Caroline is where some of those highest concentrations are measured. But a lot of those, suspended manganese particles making their way into the sediment and then being deposited in the reservoir sediments. So that's sort of a extended response there to your very important question.
A high manganese content in the groundwater, that we have arsenic content that's above acceptable levels. It's like 13 ppb.
Mm-hmm.
And so I had to figure out how to get rid of the arsenic, and there's a way with hydrous iron oxide, I guess. But
Mm-hmm.
manganese and iron interfere with that process. And so what I had to do is to find a 3-filter system to first get rid of the excess iron and manganese, which is high in the groundwater. And then the other cartridge takes out the arsenic, which it does extremely well. But Todd Miller, a guy from the US Geological Survey, and I put out a little, I don't know what you want to call it, brochure on arsenic in Tompkins County, but arsenic in groundwater is another, I think, even more serious problem than manganese.
Yeah, certainly from a human health perspective, I think, yes, yes, I agree with you. Yeah.
Can I ask a question? I put it in the chat, but
Yes.
Rua has encouraged me to ask it myself. So it might be for you, Matthew, which I really enjoyed your talk, by the way, or it might be for Roxy. Why add manganese-based oxidant when trying to remove manganese from the raw water? And wouldn't something without manganese make more sense, like hydrogen peroxide? Thanks for your answer.
Yeah, thanks a lot for the question. And yeah, you point out a very interesting, sort of almost like ironic thing here, that we actually add an oxidized form of manganese to the water to remove manganese from the water, which I think seems pretty counterintuitive when you first hear that. I actually might defer to Roxy on that one, as she was more directly involved with that decision making. If you're open to responding, Roxy.
I'm open to taking it, but apologies. I'm open to taking it, but I'm an ecologist. Chemistry is not my strong suit. This is a very common practice, though. I will say it's a very common practice in the water treatment industry. And I can't tell you the chemical equation, but it will oxidize the manganese into a form that we can precipitate. Because our first line of defense is to add a coagulant and to cause all of the solid particles to glom together until by gravity they could settle out. So if we can turn the manganese into a solid form, then we can remove it in mass for the most part. So that's what happens when you add it. And I apologize for not knowing the chemistry, but that's why we use it. And then the second thing so that's our first traditional form of treatment. The sodium permanganate that we use is the first thing that happens. It happens at the intake. It's a milder oxidant, so it needs time. That's why it has to be fed early on to do its work. But right at the plant, right when the water comes into the facility, we also add chlorine dioxide. It's a stronger oxidant, and it can remove some more manganese if there's some left, transform it, not remove it, to a different phase. Both of these chemicals were designed to be part of the treatment phase only to address disinfection byproducts. When the plant was designed, we didn't know that there was a manganese issue at all. The plant started construction in 2013. We've been operating since 1902, and there had never been any documentation of a manganese issue. It isn't like we never measured it. In fact, in front of picking the technologies for this facility, we ran a specific test on manganese because we use membrane filtration, and the membranes can get clogged or bound up with manganese. So you want to make sure you don't have a problem. So we actually did a pilot study and there was no problem. Unfortunately, two things are working against us. The reservoir has never been dredged, so it's getting shallower and shallower, and there's more and more growth. And so when that decays, we get less and less oxygen, and climate change is increasing the droughts. And 2016 was the drought of record for this area. So it's kind of a perfect storm for us. So now these chemicals, fortunately, they do help with manganese conversion, but they're having to pull double duty, and we have to strike that right balance that Matt was talking about, and it can be challenging. Oh, and
Thank
can
you.
I add, while I have the floor, can I add that arsenic is not a problem in our drinking water? Please don't worry about that. It might be a problem in Dan's well, but it's not a problem in the city of Ithaca's drinking water.
Hi, this is Scott from the Tompkins County Health Department. I think I can quickly answer why they chose to use the magnesium-based oxidant, and it's why it's more readily used in the water industry is because using hydrogen peroxide is it's more challenging for the staff to actually apply to the water, and I think in general it's more dangerous to use, and especially to get something up and running quick. I think it would have been it was much easier to use the magnesium-based oxidant.
Thank you.
I see another question in the chat. Norm asks, can you say something about the lead levels in the reservoir water?
Yes, the lead levels. Yes, I also just want to acknowledge that I see further up in the chat that maybe some folks had problems seeing the proper slides. Sorry about that. I didn't see those in the chat at the time, so I hope that got resolved. We have not measured lead in the reservoir water, so I cannot answer that question. We have, see, this is why it's helpful when you have your graduate student present in the meeting, because they know more about what's been going on than you do sometimes. So thank you, E. So the lead concentration has been less than the detection limit. It has not been a focus of our analysis, but I guess we have seen it, or we have the capability of measuring it on the ICP-MS. We haven't seen it, which is good news.
Lead in our well is less than 1 ppb.
Yeah, I think typically when we think about lead in water distribution systems, it's usually related to the pipes themselves, right? So it's sort of post-treatment release of manganese, lead. If we think about examples in, say, like Flint, Michigan, or Washington, D.C.
Oh, I'll say again, to reassure anyone drinking our water, we just finished our regular lead testing last year, and we did an extended study anticipating some new regulations, and our results were terrific. So really, lead is not a problem in our drinking water, and yes, lead is related to chemistry happening in the pipes, which we pay good attention to.
I see that there's a question in the room. Please go ahead, Ryan.
Thanks. Thanks, Roxy, for all your work on this too. Maybe this is a question more for you as well, or anyone else who wants to take it. And sorry, it's like a rhetorical one, but like, why not just move the intake? So I just wanted, like, could you talk through that as like an engineering challenge? Like, why not just do some of the things that seem like potentially like quote unquote, obvious solutions? Just talk through that briefly.
I am actually going to kick this one to Matt Slajewski, one of the water and sewer engineers who happens to be on the meeting.
I felt that coming, Roxy. So, okay.
Thanks, Matt.
Okay, I'm Matt Slajewski, environmental engineer at the Water and Sewer Division. There are plans on paper. There's a whole set of there's a whole design set up to basically replace the current intake with a multi-level structure that Matt was talking about in his presentation. We'll have one elevated off the reservoir bottom. We'll have 2 others higher up in the water column. So that's on paper. We spent several years going through the permit process with DEC to get the permit. So we do finally have that. And now we're waiting on funding. So basically it's just to do the work for the intakes and repair the gatehouse and repair the dam. We're in the $5 million range with the dredging and everything else. We're up over 10, maybe even up to $20 million. So it's a big chunk of change that we're kind of waiting on getting.
Thanks, Matt.
I'll ask a question. I'm sorry if I missed it, but why does stratification only occur in the summer?
Why does stratification occur in the summer? Was that the question? So lakes can also stratify in the winter. it's related to the temperature in the air, essentially. And if you get like a deeper lake and there's cooler water, that's denser, it develops that way. And the reason you typically in like a deep lake would have these like seasonal overturns is related to the change in the air temperature. So that's why stratification tends to occur in the winter or the summer. But like as we showed here, this isn't sort of like a strongly stratified body of water, and that stratification is disrupted relatively easily by energy coming into the system from wind or stream discharge.
Thank you.
So I also see two questions in the chat here. So one is about the speedies permit. And I believe it's a question about whether aeration or bubbling of wastewater could remove dissolved manganese. So I'm wondering, could you clarify bubbling in which system?
Yes, thank you. So yeah, I see a lot of your research is associated with obviously the potable water treatment processes, which there's a lot that goes into that. So one thing that I've personally been working with the city's treatment water treatment system with is issues with meeting the speedies permit for manganese. Because this water, you create residuals and then that needs to be treated, and there's volumes of water that then needs to be discharged back to 6 Mile Creek. So in that, I guess along the same principle of increasing aeration and mixing, that's how you keep your manganese in solid form. Could that same principle be applied to potentially keep dissolved manganese or put dissolved manganese back in solid form where it could be settled out through the residuals treatment system?
Yeah, thanks so much for that question, because I think that's a really important question, again, for the sort of like life cycle thinking of our water treatment processes that, in both potable water treatment and wastewater treatment, we generate a lot of solid waste, like a lot of sludge. And I think what you're referring to is like the leachate from that sludge, which is really rich in manganese, because we've sort of basically like concentrated all of that manganese rich solids. And and also this also sort of makes me think back to the earlier point about the use of potassium permanganate as the oxidant, right? The use of potassium permanganate as the oxidant also means that you have more manganese in the sludge compared to what you would have if you used like hydrogen peroxide, for example, as the oxidant. So yeah, so like, in some ways this is a question sort of about like residuals management, like sludge management. And I think absolutely anything that we can do that would lead to less dissolved manganese or solid phase manganese get, to being taken in that intake water would help to address this problem. And at the same time, anything that could be done that could diminish or decrease the use of that potassium permanganate oxidant dosing would also be an important improvement in just decreasing the amount of manganese that's being collected in those residuals in that sludge. So I think that would be another like co-benefit for doing this diffused aeration mixing, which is planned for the summer. So thanks a lot for that question. Does that sort of answer the question? Do you have any sort of follow-ups to that?
Oh, it does. I certainly see the benefit of the less manganese you pull in through the raw water, the less you're going to be treating through your residuals treatment system. But I was thinking, just downstream of the potable treatment system, upstream of the residuals treatment system, is there potential for aeration to just the wastewater to, the kind of the similar principle to keep that manganese in solid form so that it settles rather than pass over an effluent weir in dissolved form.
I see. Yeah. Thanks. I mean, I think the issue is that the residuals are also very reducing. And the sludge is also very reducing because there's also a lot of organic matter there. So probably once you get into these reducing conditions, the manganese is going to get solubilized. So it's very interesting because you have this system where you have reduced manganese, which is then getting oxidized so it can settle in the sludge, but then like the sludge sort of sedimentation basins or whatever then become reducing again, and then release that manganese again. So I mean, I think anything that could be done to prevent the sludge from going anaerobic would help, but I don't know that then you have this sort of aerated sludge sort of suspension, which I'm not sure if that would help things or not.
Great. Thanks so much for discussing that.
Yes, thanks so much for the question. I see there's one more question here about sediment and aquatic plants. Here, homeless species available. So yeah, thanks for this important question, Michelle. So can you just clarify, is the question about sort of like plant macrophytes growing in the reservoir, like the trophic status of the reservoir?
So as Roxy mentioned and sort of alluded to, I am the person who, let me just step into a quiet space. I'm the person that takes care of the water chestnut and all the other aquatic invasives. And so my question stems from the fact that you mentioned that there's bioavailable manganese, and the notion that definitely there's increasing sedimentation from each one of the small tribs coming in, as well as 6 Mile Creek main stem, because we've definitely, I'm sure you've seen all the islands formation and all of that going on, as well as the upstream erosion going on. So it's just telling that story to its fullest because there's influx of stream sediments and influx of plant matter decay and growth. And so there's an ecological story to be told with that. That's where I'm going.
Sure. Yeah. Thanks so much for that question. Yeah. So, I mean, I think absolutely. If you have these high levels of dissolved manganese in the pore water of the sediments where there's emergent macrophytes, emergent vegetation, or also if there's dissolved manganese in the pore water where there are some of these like sort of emerging sort of wetland areas in that southern end of the reservoir, you probably have a very active sort of like plant uptake of manganese, and then sort of re-release of that manganese as those plants decompose and decay. Yeah, I sort of, I'm a little bit familiar with this from some of my other research on arsenic and rice. So, thinking about how geogenic contaminants can be taken up into different types of plants. In this case, people aren't eating some of those wetland plants, but there's a very interesting sort of like ecological, plant uptake and then re-release into waters as those plants decompose. That's an interesting cycle, and it would be for sure interesting to learn more about what role that could play in the overall sort of like transfer of manganese between different compartments in the reservoir. Yeah, thanks for the question, and thanks for bringing that to everyone's attention.
Thank you everyone for coming today. We don't have time for any more questions, unfortunately, but feel free to send it to us and we'll try our best to get them to Matt and get a response to you. The recording of this will be available very soon, and we'll send a follow-up email with it. And we'll see you next Thursday for the next talk. Thank you so much.
Thank you everyone for the very active discussion. This was really enjoyable.
Thanks everybody. Thanks guys.